Well, good morning, everyone. It's good to be with you. I think I'd like to just dive straight into what's going on because I'd like to leave the second half of class for an activity if we can. Let's just dive straight into the material. When we were together last, we were talking about the ratio test. We did a couple examples, and then we left off kind of having just set the stage for one of the more interesting examples that's going to use or require Hopitals Rule. So let's just look straight in at that particular example. So we're interested in knowing whether the sum from 1 to infinity of n to the n over n factorial converges or diverges. And we're going to do this by using the ratio test. So to do this using the ratio test, we need the limit as n goes to infinity of n plus 1 to the n plus 1 over n plus 1 factorial. And then we're going to multiply by the reciprocal of this thing for the previous term. So we'll have n factorial over n factorial over n to the n. N, can you help me simplify? N factorial over n plus 1 factorial would be what?
N plus 1.
In the denominator, right? Okay. And then in the numerator, we still have an n plus 1 raised to the n plus 1. And then in the denominator, we still have an n to the n. Notice you have the n plus 1 in the denominator and the n plus 1 to the n plus 1 in the numerator. One of these n plus 1s cancels, leaving you with the limit as n goes to infinity of n plus 1 to the nth power over n to the nth power. Which could be written as the limit as n goes to infinity of n plus 1 over n, all raised to the nth power. Any questions so far? Very good. So we can simplify this fraction and write it in a somewhat more familiar form, or at least more mathematically famous form. And that would be 1 plus 1 over n to the nth power. And we notice that as n goes to infinity, what happens to that base? 1 plus 1 over n. That base approaches, 1 over n goes to 0.
Yes.
Yes. Sorry, I need to pin my view.
Doesn't 1 over n eventually converge? Oh wait, no, it can't because of the infinity.
So the 1 over n is going to converge, is going to approach 0. So 1 plus 1 over n is going to approach 1. And of course, n is going to infinity. So this is approaching 1 to the infinity. And 1 to the infinity is what?
1.
Not 1.
1.
It's not 1.
Indeterminate.
It's an indeterminate form. And whenever you have the indeterminate form, so any of them, whenever you have those indeterminate forms, then you know you're going to have to need to use either some version of algebraic cleverness, or you're going to have to use what? L'Hopitals rule. So L'Hopitals rule, as you may or may not remember, requires Hopitals rule requires indeterminate forms, and it only works with two forms. It works with either the form 0 over 0 or the form infinity over infinity. Really, this could be a plus or minus. Okay, so these are the indeterminate forms that L'Hopitals rule will work with. We have the indeterminate form 1 to the infinity, so we're going to have to do a little bit of cleverness before we can bust out our L'Hopitals rule. So just to start over, since we're on this blank sheet of paper, L'Hopitals rule is going to require that we take what along the way?
Derivatives.
We're going to have to take derivatives. That's exactly right. And since we're going to have to take derivatives, we're going to need a continuous variable. So we know that our stuff from the previous page is equal to that same expression, but now with the continuous variable x. And again, the reason why we're switching from n to x is because we need a continuous variable in order to use L'Hopitals rule down the road. This still approaches 1 to the infinity. So we're gonna have to be a little bit clever. Anytime you've got stuff with problems in the exponent, then you should be thinking to yourself, maybe I can use logs. So this would be equal to the limit as x approaches infinity of e to the ln of 1 plus 1 over x to the x, like that. And we can do a couple of things here. We can bring our limit inside the exponential. So it was out front here. Now it's inside there. We can do that because limits can be carried through continuous functions. And then we can also bring that x out front of our ln. So here's the x in the power. It's now an x out front. And at this stage, you'll notice that at least the exponent is approaching infinity times the ln of 1, which is 0. And tell me about infinity times 0. Infinity times 0 is also a indeterminate form. We still need to use L'Hopitals rule. The problem is we're not in a place where we can use, like in one of the right forms to use L'Hopitals rule. So what do we do in order to be able to use L'Hopitals rule here?
Another derivative?
We can't take our derivatives yet because it's not in the correct form for it. We have to still use our algebraic cleverness. How do we rewrite this thing so that we can apply L'Hopitals rule?
I think we can take x to the x inverse, I guess, 1 over. So ln 1 over.
So we can write this as
over 1 over x.
Yeah, like this. So we can rewrite the x in the numerator as a 1 over x in the denominator. Notice now our numerator is approaching 0 and our denominator is approaching 0. So we do indeed have that 0 over 0 indeterminate form. Questions so far?
Is there any way to like change it to actually so it's not indeterminate, or
Not
it's just
we're just sort of stuck with this long approach. Yeah. But from this stage, it's an indeterminate form, and now we're going to be able to use Hopitals Rule, which will resolve the indeterminate form.
Oh, okay.
So just hang in there a little longer. Okay. So now we're going to use Hopitals Rule. So this thing is going to be equal to, and remember when we use Hopitals Rule, we put the little h above the equal sign so that our work makes sense. And so we have e to the limit as x approaches infinity of, and now we got to take the derivative of the numerator, which would be, it's going to be long and ugly. I should have given myself more space. 1 over 1 plus 1 over x times the derivative of the inside, which would be negative 1 over x squared. So all this is the derivative of that numerator part. I don't know if I can do box prime, if that even makes sense. Well, I guess I could put the prime up here. That would make more sense. Okay. And then we take the prime of our denominator, and the prime of our denominator will be negative 1 over x squared. That's the prime of that denominator. Good news, terms cancel. So we have e to the limit as x approaches infinity of 1 over 1 plus 1 over x. Numerator is approaching 1. Denominator is approaching 1. And so the whole thing is equal to
E.
whole thing is equal to E. What is important about E in this case?
E bigger than 1.
E is bigger than 1. Good, Jason. So E is bigger than 1. So what?
So it's going to be diverged from the ratio test.
Exactly. Therefore, sum from n equals 1 to infinity, n to the n over n factorial diverges by the ratio test. Very good. Whew. Questions about all of that? So in my experience, this particular bit right here is, it's not hard, but it's long enough and there's enough notational detail that students can get turned around a little bit. Add on to that the fact that, you know, as we even saw in our own class, a lot of students struggle to remember what's going on with the indeterminate forms. And so I think you can definitely expect to see one very similar to this on the assessment, not this week, but next week. And it's not a trick. You just have to be careful and not fall for the traps of the indeterminate forms. So just kind of a heads up of something that's coming. The video's available, the notes are there. I'm happy to meet with everyone and go over it in office hours, et cetera, et cetera. So don't worry, you're going to be just fine. You got over a week to try to think through these things, but just a heads up that this is a famous question, and it's not supposed to be your death fate, but it is nevertheless something to look forward to. And Jason, we do have an assessment this week. I'm just saying that this will not be on the assessment this week. The assessment this week ends with the alternating series test, no ratio test. Wow, it's nice to see in the chat how excited everyone is about this particular example. Let's go do something that's maybe a little bit less onerous. All right, so we talked about the ratio test. Let's also talk a little bit about the root test. The root test is very similar to the ratio test in its formation. Basically, it says if a limit is less than 1, then the series is absolutely convergent. If a limit is bigger than 1, the series is divergent. If the limit is equal to 1, then the root test is inconclusive. The difference is that the expression is now the limit of a root rather than the limit of a ratio. Hence, it's called the root test. It's not a super, it's a super easy test, generally speaking. It's not super powerful because it really only tends to help when you're in situations like this, like the ones in the examples where you have a clear nth power. It's like if you see an nth power on the entire expression, then by all means go and consider using the root test. But except for in that one situation, it's not quite so helpful. The ratio test is a little bit more powerful, or at least more commonly used. So questions about the wording before we do a couple examples?
I have one quick question. Could we have used this on the previous problem we just did when we got to the point where it's 1 plus 1 over n all to the n? Or yeah.
Let me.
When there's that one point where the whole thing was to the power of n. Would that have been useful there?
I think
it was before we used Hopitals
really
Rule.
early on. I think it's right
There.
right here.
Yeah.
So what do you think? Could we have used the root test here?
No,
Why do you think it wouldn't work, Vu?
because we are in the halfway. we already applied the ratio test at the beginning.
Yeah.
And we're in limits, not sigma.
That's the big thing, exactly what Enrique said. Here we're looking at a limit.
Mm-hmm.
The ratio test and the root test both apply to a summation.
Got it. Okay.
Yeah. So I think your question is a reasonable and logical one and maybe common one, but yeah, it won't apply, sadly. All right, let's look at some examples. So in this case, this is 8a, the summation from n equals 1 to infinity of n over 2n plus 3 all raised to the nth power. I'm like, wow, there's an nth power. We want to fight the power. So let's use the root test. You guys are playing Animal Crossing during class? That's kind of sad, Joseph. So we're going to have the limit as n goes to infinity of the nth power of n over 2n plus 3 raised to the nth power. And you'll see that the nth root or nth power and the nth root take each other out. All that morbidness that you all talked about with the last example comes into play. And so we have the limit as n goes to infinity of n over 2n plus 3, which is a funny way of writing what?
0?
The other 0.
Over 2?
1 over 2.
Oof, that
Right?
was tough.
Same degree on the numerator and denominator. What's important about 1/2?
Less than 1.
Less than 1. Very good. So less than 1. So what do we conclude?
Oh, the lack of confidence. I'm going to go for it that it converges
And how do we know it converges?
because it's less than 1.
At the root test.
Okay, yep, converges. Let's add one word here, by the root test. I think I forgot it in the last example. What's the word that goes here?
Absolutely.
Absolutely, that's absolutely right.
Wait. But we don't have absolute values.
They weren't, we could have put them in up here. I think right here, but I could have put them in, but because there was no negatives, I just ignored them.
Okay.
Yeah, got a little fast and loose. Questions about this? All right, let's look at one more example. So here we do have the negative in the summation. We still have the nth power. So the nth power tells us to use the root test. And this time, because I have the negative, I will indeed put in the absolute values. So here's those nth powers and the nth root that are gonna take each other out. The absolute value is super nice. It's gonna take out that negative. So we have the limit as n goes to infinity of n plus 1 squared over 3n minus 6, which is what?
Infinity.
Infinity. And what's important about infinity?
Greater than 1.
Yeah, it's a little bit bigger than 1. So since it's bigger than 1, what can we conclude about our series?
Diverges, absolutely.
It's and that would be true. We don't need to add the absolutely with divergence, but it's absolutely true. And using which test?
Root test.
By the root test. Questions? So I think what you can see here is that the ratio test and the root test tend to be both very powerful and very straightforward. The one time that they get challenging is if the limits are challenging. And so you just got to be careful with your limits. We can create some scenarios where they're a little bit more challenging to work with. But basically, the ratio test and the root test are very powerful. They're relatively easy to use. And the times when they're difficult are times when you have to just be careful with limits and you end up with indeterminate forms. So any questions about the ratio test and the root test, or should we do something pretty cool?
I like cool things.
I was thinking the same.
I like cool things too. This is one of those things that I think the first few times I taught the class, I just sort of missed it. And then a couple years ago, I discovered it in the material and was like, oh my gosh, where have you been my whole life? This is just so bizarre, like one of those mind-bending math things. So do you remember what the name of this series is?
Alternating harmonic?
Exactly. This is the alternating harmonic series. And what is it equal to?
Pi over 3 or something?
No pi's in this one, I don't think.
ln of
Is it?
Yeah, this one's the one that's the ln of 2. Yeah. There was a pi squared over 6 that showed up, Croy, so you're not crazy. It showed up in another one. So this one's equal to the ln of 2. Now what I'm going to do is I'm going to rearrange the terms. Okay. And it's going to take me a few steps to get there. So to start with, what I'm going to do is I'm going to take that original series and I'm going to multiply by 1/2. So if we had 1/2 ln of 2, in order to get 1/2 of ln of 2, I could just multiply all of these terms at the top by 1/2. Everybody tracking? So the 1, so it'll be 1/2 minus 1/4 plus 1/6 minus 1/8 plus 1/10 minus 1/12 plus ... Questions so far? Very good. All right, so then now I'm going to play one of the oldest tricks in the math book. I'm going to add zeros. And so I'm going to put a whole bunch of zeros into this expression just to help things line up. And so here I have 1/2 minus 1/4 plus 1/6. So I'm going to say that 1/2 ln of 2 is equal to 0 plus 1/2 plus 0 minus 1/4 plus 0 plus 1/6 plus 0 minus 1/8 plus et cetera. You see how the terms are showing up? There's 1/2 minus 1/4 plus 1/6 minus 1/8, et cetera, et cetera, et cetera. Questions so far? Okay. So let's take this series and let's join it with the one that we started with. So we have, remember that we also have 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/7 minus 1/8 plus ... And remind me, what's this top line? What's this line equal to? It's
1
written
ln of 2.
ln of 1/2
Yeah.
ln of 2.
1/2 ln of 2. Good. And what's the bottom line equal to?
ln of 2.
ln of 2. Okay. So here's 1/2 ln of 2. Here's ln of 2. And so if we put these two things together, we should get an expression for, one would think, 3/2 ln of 2, right? So we're going to get, if we add these together, so 3/2 ln of 2 would be 0 plus 1, which would be 1, plus 1/2 minus 1/2, so plus 0, plus 1/3, minus 1/4 minus 1/4, so it'd be minus 1/2, plus 1/5, 1/6 minus 1/6 plus 0, 0 plus 1/7, minus an eighth would be minus a fourth. Dot, 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 dot. Let's clean that up and get rid of the, get rid of the 0. So this would be 3 over 2 ln 2 is equal to 1 plus a third minus a half plus a fifth plus a seventh minus a fourth plus dot, 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 dot. Here's 1, here's a third, here's a fifth, here'd be a seventh. And I don't have enough space to keep going, but I think you can probably see pretty easily based on this work that the series at the top and the series at the bottom are the exact same series. They're just in different orders. I've just rearranged the terms. And yet the one at the top is equal to ln of 2, and the one at the bottom is equal to 3/2 ln 2. I just rearrange the terms and I get different values. Mind blown. Mind blown. So more generally, the mathematician Riemann proved that if a series is a conditionally convergent series and R is any real number, then there's a rearrangement of the series that sums to R. So here we showed that we could rearrange it to equal 3/2 ln of 2, but Riemann proved that we could have made this equal to any number we wanted. Pi, half pi, negative numbers, positive numbers, it doesn't really matter. That's nuts. But it also explains why conditional convergence is such a big deal, like why we talked about that and we're careful around conditional versus absolute convergence. And it also helps you understand why mathematicians were so confused by divergent series, as you're reading about in the essay that you're talking about today. So there's some crazy mind-bending things that are happening with infinity. And this is a nice hint of that. Thoughts?
So this is talking about the fact that it's conditionally convergent?
The original series was conditionally convergent, and because it was conditionally convergent, we could rearrange the terms. It would still be conditionally convergent, but it would have a different sum. Crazy stuff. Yeah, it doesn't mean you just, yeah.
The math doesn't lie.
The math doesn't lie, but that doesn't mean that it makes sense. Doesn't mean it makes sense. And I think it's one of those places where the more you think about it, the more perplexing it is.
The best part for me is that, like, if I had found this, I'd be like, oh, well, that's just obviously wrong.
Mm-hmm.
And not like found some awesome like theorem based on it. I just like, yeah, that's totally wrong. I like messed up somewhere.
Yeah, exactly. You wouldn't assume that this was because you discovered some great insight. Totally. Yeah, totally cool. All right. That's it. We've made it through the whole list. You now know all the way, well, not all, but you know all the ways we're going to talk about in this class for determining if a series converges or diverges. When we come together again on Tuesday, we'll talk about how to recognize which test might be most helpful to you in certain situations. But you sort of kind of now know everything that you need to know. And I hope you now also know some of the theory and nuance behind the power series that you were playing with back in Calc 3.